here we have radioactivities. So what is radioactivities? Radioactivities is what is the spontaneous decay or disintegration of the nucleus of the atom of an element, during which it emits the alpha, beta particles and the gamma ray, or the combination of any of all these three energy. You understand? Or heat. Is it that you say energy or heat? So now we have types of radioactivities. Moving on, we have the natural radioactivity and we have the artificial radioactivities. So you having two types of radioactivities, you'll be able to differentiate between the two types of radioactivities we have. So moving on, we have that. What is the natural radioactivities? As you can see clearly, this is the spontaneous disintegration of the nucleus of an atom, during which alpha particles or the beta particles or gamma rays or a combination of any or all the three and heat or energy are released. Okay, so what is artificial? Artificial radioactivities is a kind of radioactivities which involves an ordinary material not normally radioactive, made radioactive. They are not normally radioactive, but they are made radioactive by what? By what means are they made radioactive? By bombarding it with radioactive particles. That is the only way you can make it a radioactive, by bombarding it with the radioactive particles. Is what we call artificial radioactivities. Now moving on, we have what we call radioactive elements. What are radioactive elements? They are elements which spontaneously emit radiation from what? From their nucleus. They emit what? Radiation from their nucleus. That's a radioactive element. For example, we have examples of radioactive elements. We have radium, we have thorium, okay, we have radon, we have ionium, we have polonium. Again, I said the examples of radioactive elements we have radium, we have thorium, we have radon, we have ionium, and we have polonium. So moving on, we talk about half-life. Okay, so what is half-life? Half-life is the time taken for half of the atoms initially present in the element to decay. Again, I say half-life is the time taken for half of the atoms initially present in the element to decay. And you know fully well that the word disintegration means to decay. The word disintegration means to decay. So I am going to give us a profile of a radioactivity, the sketch, the diagrammatic profile of radioactivity that really define the word decaying half of the given atom. But before then, I have to expatiate on this guy, half-life. So half-life has a symbolic denotion. So the symbol for an half-life is capital letter T. I said we have a capital letter T like this. You know, literally, this capital letter T is representing something in physics already, that's period. But we borrowed that same alphabet to be standing in as what's your half-life. There's a difference between this capital letter T and small letter t. This one is time taken for half-life, and this one is time, that this one is half-life. You understand? So moving on, I'll be explaining half-life further. Okay. All right. So now moving on, we have another, okay, the equation for half-life. So mathematically, under half-life, so we have this equation like half-life is equals to time taken to decay, or time of half-life over what? N. Okay. The second formula for half-life is T is equals to, sorry, I'll call you back, I'm on live. T is equals to small letter t over log of r base 2. Okay, so we have two formulas for half-life. We have this and we have this. Okay, so represent this one letter c represent time taken for what? For a radioactive element. to decay. I'm taking for a radioactive element to decay, but this capital letter T represents half-life of radioactivity. And you have to note that this R here, it has a formula, but you know that this R here represents disintegrating ratio. Okay, this R here represents disintegrating ratio. That's the meaning of that R. So I've told us what small letter T is, I've told us what capital letter T is, I've told us what capital letter R is, and this N here is number of what? Number of half-life. N represents number of half-life. Note those things now. So remember, I was going to talk about something that should note something. So in case you are not given R and you are told to find half-life, so R has a formula, disintegration ratio has a formula. Either you use this one, disintegration ratio formula is either 2 raised to the power n, or you can say R is equal to n1 over n2. Okay, so this is the two formula for disintegrating ratio. You have to note it down in case you might probably not be given disintegration ratio in a question and you are told to find half-life, so that you will be like, how do I go about this? So these are the formulas for disintegration ratio. This n, remember, it represents number of half-life. Then this capital letter N1 here, N2 here. This one is the initial atom, this one is the final atom. Because by the time you begin to disintegrate, you disintegrate any atom by half. So I will draw the diagram for a radioactivity, the profile of a radioactivity. You are going to understand what we are talking about. Whenever you want to disintegrate, you disintegrate by half. If I have n atom, if I am to disintegrate that element, that will be n multiplied by half, and I have n over 2. The more you disintegrate, the more it reduces. You understand? So that brings us about making n1 to be greater than n2. Understand? So the disintegration ratio is also the ratio of what? The disintegration ratio can be defined as the ratio of the initial atom to the final atom. You can use it that way, because I told us in the physical class that most times in life, you see physics, you can get your equation from your definition, and your definition can make you to get a clue for the equation. You start taking on. So that is that about that. So note all these things very well. And let me talk about this time of half-life. Your time of half-life can be days, it does not have a particular unit. So regardless of anything that has to do with time, anything that has to do with time in this life, like months, days, year, decades, anything, regardless of any unit it have, it is still, so that you can be able to say that which one is mighty inside this question. So anything that has something like month, days, year, maybe seconds, all those things, you should know that they are your small letter T. So it does not have a very specific, okay, like we used to say that the unit for time is seconds. So the units can come in any form. There's no need for conversion. Just use it straight up. Alright, so I will stop at the profile of radioactivities before we now begin to solve questions. But before then, this is an introduction of radioactivities. I'll draw the profile, I'll give the other definition. Then on the next video, you are going to see calculation, strictly calculation. I want you to pay full attention. Alright, let's move on. Decay curve and half-life. So we can call it radioactivity profile. So it goes this way. This side, okay, this side is our time, this is our time, and these are our atoms. It can be your atoms or molecule, depending on what you have. Alright, so I have this like this. This is the curve. This is the curve. So it is just like a normal demand curve. Okay, I have this like this. So suppose this is our n. The beginning we have n. So, and this is, okay, this is your n, this is your n naught. So what will be this place? If I disintegrate this guy, what do I have? I should have n naught divided by 2. Again, if I further disaggregate this, remember I said we decay by half. Abi, it's not necessary you put this n here. What I'm trying to say is that this vertical axis is representing n, and this side is representing what? Time. Are we together? It's representing time. But what type of time? Half-life. It's two different type of time we have. We have T and we have. They are both time, but this time is called half-life, and this one is called time taking for something to decay. So I'll call this one my T. Okay. So whether regardless of the T I have, there's nothing like T1, T2, this. Everything is just T. It is uniform. Everything is just T. So what will be the atom for this T here? For this half-life here, the atom is going to be n/2 because I disintegrate this n0. Here I have n0. So if I disintegrate it, so we disintegrate by half. So n0 multiplied by half, I have n0/2. So if I further disintegrate this one again, I want to disintegrate n0/2. That means I have to multiply by half again. So what will I be having? I'll be having n0/4. You understand? n0/4. If I further decide to drag another one like this, like for instance, I decided to drag another one like this. It depends on you. You can stop anywhere. You can stop here. So it depends on you. So if I further disintegrate this guy again, that means I have to multiply this guy by half again. So what will I be ending up with? I'll be ending up with n0/8, but it still remain my normal T. So you see in your textbook, you can decide to stop at any n, subsequent n they like to stop at. So that is clear about the graph of radioactivity. That's how radioactivity works. Disintegration means to decay. Understand? So I'm now going to just give you some tips that might come out in jam. But let me first define. Do I need to do that? Decay constants. Let me define decay constants. It is very necessary. I define decay constants. Let me give us the definition for decay constants. For decay constants, so that the next work will be a relief. We are not going to do much work. Decay constants. Decay constant. Decay constant. Alright, so in this side, what's decay constant? This is defined. This is defined as the instantaneous rates of decay. Instantaneous rate of decay per unit atom of a substance. So it is denoted by lambda. Alright, it is denoted by what? By lambda. It is denoted by lambda. That's the symbol. So I'll be giving us the formulas. Okay. Mathematically, we have that this guy, the first formula is number of atoms disintegrated per seconds divided by number of atoms in the source at that time. Okay, I prepare some notes. So the next formula is lambda to be equals to is 0.693. You understand? Over T, which is also, or lambda equals to lim 2 over T, because lim 2, if you type your calculator, lim 2 is the same thing as 0.693. So that is where I'm going to be stopping for today. Okay, so study this very well. Know the definition for your decay constant. Know the definition for those ones I've talked about. So you have two formulas for decay constant, and I've given formulas for half-life. I've given you the graphical gravitational profile for radioactivities. So I think with all this is the introductory part. So you should be able to say something about radioactivities. Anyway, I go by the name I like tutor. So this is my phone number for those of you that want to message me, +2347059676430. Alright, so don't forget to